Okay, so one more quick video just to cap off acids and bases before we move on to the next topic. And I want to talk about pH measurement. And there's sort of two different major ways. There's lots of different ways, but two major ways that we would measure pH of aqueous solutions. The easy way during a titration is to use these color or colorimetric indicators, these dyes, and the other way is to use a pH meter. So when you don't have a meter, indicators are nice, but how do they work, right? You've used them even in this class already. What's their functionality? Well, hopefully it's no mystery to you that these are just simply additional acids and bases, which have their own pKa values associated with them. So I have up here just a really common one in its molecular form. This is Thymol Blue. And so Thymol Blue is actually this compound, the fully protonated compound here. But notice that it's red, the color of it's red, but the first pKa is 1.7, so it's only red below 1.7. Above 1.7, where the molecule becomes deprotonated, and you end up having this species that is yellow. And then the sort of more important pKa, which is 2, is 8.9, and that's the transition between yellow and blue. And if you've used Thymol Blue, you've used it because of its second pKa, because rarely, if ever, are you doing a titration of some acid or base that has a pKa this small, right? This is essentially a strong acid, so we're not typically titrating where the end point is 1.7. So how does this thing work? Well, I mean, if you think about this, right, at pK, if you're doing a titration, and maybe you're titrating a weak acid, you would have a curve that looks something like this, where you have pH here, and you've got some milliliters of base that are being added, and you're starting out down here. Whether this is actually the simulation that I have here is actually a strong acid being titrated with a strong base. We know that if you titrate a strong acid with a strong base, then the pH at equivalence is going to be 7, because what you have in your system at that point is just pure water that can dissociate to make protons and hydroxide at 10 to the minus 7 molar. So the way that these things work, or the way that you should think about using them, and probably in the past the way that you've used them is somebody's just told you what dye to use. So you use phenolphthalein for something, or bromothymol blue for something, etc. But you never really thought about why, right? Or maybe you thought that all dyes are equivalent, or maybe you never thought about how they actually work. Well, the whole point is that they change color upon protonation, deprotonation. The goal then for you in choosing a pH indicator dye would be to choose one where that transition, that color transition, or wherever the pK for that color transition is coincident with the equivalence point pH of your titration, right? Because your whole goal in seeing a color change in a titration is observing when the equivalence point occurs in a solution, right? And so you're using the color to tell you that. And so you need that color change to occur exactly when you want it to occur. That means you need to choose a dye. That means you need to understand first the nature of your system and where the equivalence point should occur, whether it's going to be an acidic pH, a neutral pH, or basic pH. Then you need to look at a table, something like this, though there are much larger tables than this. You need to look at a table and choose the dye that undergoes a pH change closest to where you expect the equivalence point pH to be. In the case of the simulated example that I have here, if we're titrating a weak or a strong acid with a strong base, we know the equivalence point is going to be exactly at 7. If we look at Thymol Blue, which we have up here, we know that's going to go from a yellow to a blue transition at 8.29, and that's what we see here. Is this yellow to blue transition, which is actually considerably above where the equivalence point pH would be. In that case, when we are doing this titration, we don't mark that titration as done until the system reaches a pH of here, which means we're adding a slightly too much base to the system beyond equivalence, right? That's where error manifests in using indicators. If you can choose a dye from a table like this where its color change resistant is exactly at the pH that you would expect, then you're going to minimize the error, and that's the goal in choosing a dye. If you were, say, to choose, I don't know, let's say, for example, thymol, not the, yeah, let's see, let's say methyl orange. If you were to use methyl orange for this titration, then you would toss this into your strong acid. It would be yellow, and you would never see a titration as you moved up, right? That's not even error, that's just incorrect. Let's say you chose alizarin yellow R for the strong acid strong base titration. In that case, the transition goes from yellow to red somewhere in the pH 11 range, so somewhere up here. In that case, you would keep adding base until you saw this thing go red, but at that point you would have added this much more volume than what the equivalence point. But you wouldn't know that, right? Because your sensor is this dye change, and that's all you have. You have nothing else to tell you. And so you can start to see the importance of choosing these things. On top of all of this is the random error. So the choice of your dye could be manifest as a systematic error, right? In the case of choosing alizarin yellow, that's a systematic error because you're systematically always going to overestimate the equivalence point volume. But even if you chose something that was pretty close, say you're choosing Thymol Blue in this case, it's pretty close, you're going to have built into that the random error associated with human perception of color change. If you have 100 people all doing this titration, they're going to see these colors slightly differently simply based on the anatomical construction of our eyes, our retina, and the cones that give rise to color in our eyes. And so that's a random error manifestation, in which case color indicators for titrations are always going to be that way. Color indicators are simply convenient, but they're not the best method, as you see, to measure the concentration of protons in solution. The best way to do that would be to use a pH meter, but pH meters also have error associated with their measurements. We're going to talk about that in a later chapter when we talk about potentiometry. This is all I want to talk about in this video. So, in terms of assessment, how I want you to think about this is intuitively. I may give you a titration. I may ask you to choose a particular dye, or I may ask you something about error associated with the dye choice in a particular type of titration.